Hello and welcome, Algebra 2 Accelerated. So this is our lesson 3.1. So we're going to jump right into it. So first of all, we're going to make my face smaller because who needs that? And as you can see, I'm already logged into our textbook. So if you hit this button over here, the Discover, Module 3, that's where we're at. We're going to scroll down. Lesson 1, Graph Polynomial Functions. So I'm going to walk us through the interactive lesson. You all should have access to the interactive lesson as well. So you can look over it whenever you want. You should also have access to the textbook, which is the quote-unquote non-interactive version of this. So section 3.1, Graphing Polynomial Functions. So when they're talking about polynomial functions, we're talking about things like x cubed, x to the power of 4, and we're going to try to graph these things. So an example of when we might use this. So let's say Emmett wants to put a fish tank in the middle of her science classroom for maximum viewing potential. He is looking for an aquarium with a 360-degree viewing area, aka a cylinder. And so if you know anything about volume, you know that the volume of this cylinder is going to be based on the radius of the circle inside of it, and it will probably be cubed. So by looking at that graph, we can answer a lot of different questions. Things like how much water might fit in it? What's the volume of it? How much is that water going to weigh? So things like that, simply by graphing or working with an x cubed function, we can work with that. So let's jump right in. Maybe. So as always, we're going to start with the parent function. And in this, we've already talked about ax plus b, that's our line, ax squared, and all this stuff. That's a normal parabola. And here we are with an x cubed. So our parent function is going to be right here. So basically, f of x equals x cubed. So as we go down, this is the graph of f of x equals x cubed. Notice how it's got our vertex in the center there at 0, 0. And it goes up one way and down the other. And if you were to chart some values out for x, here's all of our x's. Here's what they would equal. And again, they would be on this graph somewhere. So some things we could notice, as a quick review, we could talk about the domain of this. Domain is going to be all x values, because even out here, there is an x value that would be defined. If you want to double check it, you can always do 100 cubed. Does that value exist? And the answer is yes. I'm not going to figure it out, but yes, it does exist. Does negative 100 cubed exist? Yes, it does. So our domain is all real numbers. Our range, which is again our y values, all of these guys. So this is where it's going to differ from a parabola, but this is also all real numbers. Because a parabola just goes up like this, whereas our cubed function goes down. So it does include all real numbers. And as x approaches infinity, f of x is going to approach infinity. And as x approaches negative infinity, f of x is also going to approach negative infinity. So that's good to know. And also increasing, decreasing. Remember, we kind of talked about that. If we go back up here, That's the one I forgot. So this graph is actually increasing the entire time. So as you move left or right, it's going up, going up, going up, going up. It levels off, but it's still kind of going up, and then it goes up, goes up, goes up, goes up. So it's always increasing. So which is a little bit different than our parabola. So we're going to wait for this to load. So when it says graphs of parent polynomial functions, so that's just a fancy way of saying x to the nth power. So you'll notice here all of this stuff. That's, again, just a fancy way of talking that we're going to go to the higher degrees of our x values. It also notes things like x to the 0th is equal to 1. So you'll notice this last value is just a normal 1. So that's why they that's why they drop the x value off of that. And just so you know, polynomial functions of degree 4 are quartic functions. Polynomial functions of degree 5 are quintic functions. Things that you should always know. So here is just a variety of different graphs. You'll notice f of x equals x, x cubed, x to the 5th. And then on the right, you see x squared, x to the 4th, and x to the 6th. So you'll notice on the left, all of these are odd functions. So x to the 1, x to the 3, x to the 5, so on and so forth. Everything on the right are even functions. So by looking at the graphs, again, we can figure out things like, the n values. So the n values of all odd functions, you'll notice as x approaches negative infinity, f of x is going to approach negative infinity, and then the opposite on this side. Whereas even functions, both sides approach positive infinity. So again, that is true for all odd functions and all even functions. So that's kind of important to remember as we're moving through. It turns out we can kind of do a lot of the same stuff we've been doing with our quadratics, just with odd or even functions. So that's again why we'll spend a lot of time with x to the power of 3 or x cubed, just because all of these odd functions will behave in a very similar way. And fun fact, x squared, hey look, that's even, so the function is going to be even. So I think they did that on purpose, which is kind of nice. Okay, so we've learned some stuff about odd and even functions, so how is it all going to play out? So this chart is what's going to kind of help us out. So we're going to be doing some transformations based on parent functions, similar to what we did with in Modular 1. So we all had so much fun with that, we're going to do it again. So get comfortable. So what we're generally going to do is we're going to use this chart, and let's say the new graph gives us 3 points. It's most likely going to give us the vertex, and then a point to the left, and a point to the right. So we can use this chart. So this is, the left side is the parent functions, the right side would be the g of x, or the translated function. We can use this chart to then use algebra to figure out what a, b, h, and k are, and then from there we can graph the function, answer questions, so on and so forth. So as we move down, identify the transformations of the graph f of x equals x cubed. That produce the graph of g of x. equals 1/3 x plus 1 cubed minus 2. Then graph G on the same coordinate grid as G of F. So remember this guy? So this is our chart that we had in Modular 1, or Chapter 1. And using all of this stuff, it's the same process for x cubed. So looking at our equation right here. So from there, we can see that we've got an A, which is equal to 1/3, which again is going to be a vertical stretch, or I guess a vertical compression by a factor of 1/3. We've got a, looks like we do not have a B. So notice our B would be right here. And so in that case, our B is going to be equal to 1. So then our plus 1 right here is going to be our minus h. So if we were to add a number into h to get it to plus 1, we would stick in -1 to change that sign. And then our plus k right here is going to be our minus 2. So k equals -2. If you don't believe me, obviously they have, this is a worked example. The answer's right there. So based on that, we can then graph our function, right? So let's see here. So this is all the exact same thing that we were just kind of talking about. So using this graph, or using this chart, A relates to a, I'm just looking up here, a vertical stretch or compression. B relates to a horizontal stretch or compression. And H relates to a horizontal translation, and then K relates to a vertical, or a vertical, either up or down translation. So describe how the graph of G is related to the graph of F. So again, this is just kind of all what we already talked about. So here is where, this is what you're going to kind of see in your homework. So in order to graph the function, so especially with like the vertical compressions and horizontal compressions, like how much does it compress? It's kind of hard to see. So that's what I had mentioned earlier. You're going to make a chart like this one, where our parent function, again, you're going to use x equals -1, 0, and 1. And then you're going to use our g of x function, and you can algebraically solve, or, I mean, in this case, since we have the a, b, h, and k values, you just plug them in, and then you get some points that you can graph. So in this case, our blue is our parent function, and you'll see the 3 points that they picked. Again, -1, 0, 1. And then our new function, they used, so if we start here with our vertex, you go over that way 1, our middle there, and over that way 1. So that's what these 3 points are referring to. So this is kind of an interesting question that they posed here. Why are these 3 points used to graph the transformation? I mean, I would just say that they're the most, they give us the most information about, whether it's going up or down, and then how far or short it's coming. Now, that being said, could you use any 3 points? Well, definitely not any 3 points. So let's say if we come back up here, if we were to pick, this point, and this point, that wouldn't tell us anything about up here. However, could you do the vertex, a point over here, and a point over here? Yeah. I mean, it wouldn't be as convenient as using these 2 points, but they would work. You'd always need to know where the vertex is. That's probably an important one. But you couldn't use any 3 points, but there are different points that you could use. So this is one more example, or another example, I should say. Identify the transformations of the graph f of x equals x to the fourth. That produces the graph of g of x, and they give us an equation. Then graph g on the same coordinate grid as the graph. So this is the exact same thing we did, except for it's using x to the fourth as opposed to x cubed. So again, using our wonderful chart here, you can extract all of these values. They give us our values right here. So then we can use those. And again, it's going to be a horizontal stretch, a translation of 3 units right, 1 units up, all based on this equation right there. And then this is the chart. This is the chart that is really the new thing in this module. Get used to using this chart, making a chart of the parent function. You don't always have to make those because those numbers are going to be very similar. But this chart right, or this part right here, is going to be very important. So again, it's to the power of 4. So, and we know all of the values in these. So we just solve for them. And then we've got 3 points that we can graph. And here we go. So our blue is our parent function. Remember, it was an even function, so it's very similar to the parabola. Our red function is the translated function. Again, just following all these steps. All of these steps should look pretty familiar from using this graph, or this chart. So does the graph of G appear to match the description based on the analysis of the parameters and values? Yes. So it increases, so it decreases down to the vertex, increases after that. It's all positive. It has the same domain range, and it matches all the parameters that they gave us. So too easy, right? So this is where it gets even more fun. So now instead of giving us the equation, they're just giving us a kind of a placeholder equation, but they're giving us the 3 points. There, and there. So now we have to use not this chart, but the one that we saw from this module to help us figure out how to graph these things. So again, if we're using this chart on top, we can, so we know this side from our parent function. Our parent function is, they told us x to the fourth, right? No, I don't remember. Yeah. So they said x to the fourth. So they gave us that. So if we're going to make our chart, f of x equals x to the fourth. So our x and our y's are going to be a piece of cake. This is the easy part out of the problem. So you've got x is negative 1, 0, and 1. When x is negative 1, plug it into the function at the top. Y is going to be 1 because it's an even function, so you lose that negative. 0, still going to be 0. 1, still going to be 1. So that's the easy part. So the not easy part is going to be this side. It's going to be this side. So you'll notice as we go from top to bottom, it goes from left to right. So this is our first one, this is our second one, this is our third one. So let's try to figure some of those out. So again, if we are looking at this chart, and I'll do it in red, x and our y. So first we got our first point, which is, let's see here, is that still going to be negative 1? Yeah. Let's double check that before I... So let's get rid of this thing. Move our stuff around so we can see everything. Okay, so our first one, we're working on this part right here. So it's negative b plus h is equal to, that's our x. Here's our x value. It's going to be equal to 0. Okay, that's cool. So as we're going down, we've got h is equal to 1. Pulled that from right there. And then we've got b plus h is equal to 2. So from there, okay, so h equals 1. So that's cool. We'll put that over here on the left. H equals 1. So then we can plug that into either one of the top equations or the bottom equation. So if we plug 1 in for the h, b would also have to equal 1. So if this were 1 right here, then b would also have to be 1 to make this a true statement. We can plug it on up here just to make sure. If that h is 1, b would also have to be 1 to turn that into 0. Okay, so that makes sense. So then we've got our y values. So we've got negative 1 to the power of 4, which is just 1. So we can kind of leave that off. A plus k. And that's going to be equal to this guy right here, negative 3 over 4. Gee, thanks, giving us fractions. So then we've got k is equal to negative 4. Got that right here. And then we've got a plus k is equal to negative 3 over 4ths. So from there, we can figure out, so if we take k shoved into that equation, so we've got negative 4, so then a would be equal to 1 over 4, right? Yeah. So then we can double check that by putting it into this top equation. Again, k is negative 4 right here. And then if you subtract the 1/4 from that, you would make that work. So again, over here on the left, our a is going to be equal to 1 over 4. Our k is equal to negative 4. So we've got all the information we need. And you'll see that's what they did right here. So they're solving for all those values that we just did. So now that we have all those values, we can plug them in. So again, these charts are going to be very helpful. So remember, we've got our, I guess, what did they say? J of x or something? Yeah, j of x. Well, we can do it right here. So we know all those letters now. J of x is equal to a, which is 1/4, x minus h, which is 1/4, plus a negative 4, which would really just equal minus 4. And that's how you do it. Too easy, right? So this process of writing the equation of the transform function is similar to graphing the transform function. Again, all of these different numbers mean different things for the transformations of the function, so it should seem pretty familiar. So again, this is just another example, except this time we are using an odd function as opposed to an even function. And so here is our new function. So we've got, from that, we can do our parent function. So again, that's going to be negative 1, 0, 1. So f of x is what? X cubed. So then our y is going to be negative 1, 0, and 1. So then we're just going to use this chart again. Let's get this stuff out of the way. to be able to figure all of this out. So again, with our f of x, we're going to have our, I guess I'll use the letter they used. What was that? J of x. So if this is our j of x function, our x, and then our y. So again, we've got negative b plus h is equal to this guy right there. And then our h is equal to this guy right there. And then our b plus h is equal to this guy right there. And again, on the other side. So let's see here. This is x cubed, right? So that's going to be negative a plus k is equal to 0. By the way, this negative a, I was looking at this right here, and negative 1 to the power of 3 is still negative 1. So that's where that came from. And then our, let's see here, let's keep our colors going, right? So our k is equal to our 1, and then a, oops. Then our a plus k is equal to this guy right here. So now, using all of that information, you just algebra this thing. Okay, so they've got all the same values we do. So you can either, so you algebra it, figure out your b, h, a, and k, and then you can write the equation of the transformed function here. So we've got one more example. This is our real world example that we always like to go over. So this is talking about these edible water spheres. So the background behind these is in a development that could reduce the consumption of plastic water bottles, scientists have created edible water spheres. The capsules that encase it is made using calcium chloride solution and brown algae extract. What is the approximate radius of an edible water sphere? With a mass of 116 grams and a density of 1.04 grams over centimeters cubed. So these are actually kind of interesting. The goal of these is, so you can buy a bunch of water, balls, edible water spheres, and instead of using a water bottle, you just pop the spheres in your mouth, bite down, and then you got a whole bunch of water. And it's all edible, nutritious. I don't know, I guess it's made of algae, so that's kind of cool. But we're going to need to find a radius based on, we have grams and we have density. And so our density, and this is by definition, for those of you in chemistry, you should already know this, is mass divided by volume. And so what we could do is do a little bit of algebra, do our volume, move it over, times density equals mass. Or we could put our volume by itself. Our volume is going to be equal to mass divided by density. Okay? So now we can write a polynomial function to model the situation. The definition of the volume of a sphere is given to us right here. So again, V of R is 4/3 pi r cubed. So there's a variety of ways that you can go about solving this problem. What they wanted to do, or what you'll see in your book, is they changed their functions to be a function of mass. So that's easy to do. We're just going to use this one right here. And so our mass as a function of r is going to be equal to our density, which is 1.04 times our volume, which is 4/3 pi r cubed. And so now you can just kind of multiply all of this stuff together to get an approximate answer. And so I'm not doing that in my head. So I'm going to do 1.04 times 4 divided by 3 times 3.14. And that's going to give me approximately 4.36 r cubed. So now we've got our x cubed function, and then we've got an a in front of it. So we can then pick some values for r, plug them in, and then of course we will get an answer. So that's what they did right here. So plug in 0, 0, got it. Plug in 1, just going to be 4.36, 2, 3, so on and so forth. So they get these points right here. And then from that, they can use the graph to try to answer the question. Which I already forgot what the question was, but yeah, what is a radius of a water sphere with a mass of 116 grams? So then this red line right here that they go across is 116, and so then you would just, this point would be the one they use. So 3 gets you pretty close. So a little bit less than 3. So this is a technique that's very commonly used in science. And so again, those of you in chemistry, this should kind of look familiar. But you make a graph so that you can kind of plot trends. You can see trends. And then you can use those trends to then make predictions. And that's kind of basically what we did here. Is we made a chart to then make a prediction. So then how does that relate to what we've been talking about? As mentioned, it is an x cubed function, and it turns out that it is just a vertical stretch of the parent function. And so we know that because our a is 4.36 is greater than 1. It's a thing that we've been talking about, and it just allows us to better understand our functions and be able to use them. So that's how we do our real-world problem. So from here, I would like you guys to try the check on learning in the assignments and see how that goes. And we'll go over the practice problems, otherwise known as homework, in class. So we're going to do all of that in class. So I will see you there. Good luck.